Hello, everyone. Welcome to our webinar today. Thank you for taking the time out of your day to be here. We will be discussing the challenges of high-speed imaging and how we address them with the Kinetix CMOS camera. To take you through it, we have myself, Rachit Mohindra. I am a product manager at Teledyne Photometrics and have been so for over 10 years now, with experience with CCD cameras, EMCCD cameras, and scientific CMOS and the back-illuminated scientific CMOS devices as well. We also have with us Dr. Dan Croucher. Dan, would you like to introduce yourself?
Hi, thanks, Rachit. I'm Dan. I'm the marketing manager for advanced microscopy here at Teledyne Photometrics, where I've been for about 4 years now. In my role, I'm mostly working with scientists directly to better understand their applications and to find out where, as scientific camera manufacturers, we can make their jobs easier or improve their imaging performance.
A little bit about Teledyne Photometrics. We design and manufacture high-end cameras for low-light biological imaging and have been a market leader for scientific CMOS technology for quite a few years now. We were the first company to introduce a back-illuminated CMOS camera to the market, the Prime 95B. In terms of history, we've been around since 1978 and joined the Teledyne Imaging Group in early 2019. So when it comes to high-speed imaging, scientific cameras are fast, you could say, right? A typical CMOS camera, as we've all kind of come to expect, is a 4-megapixel device that does about 100 frames per second. And yet, when I've gone out to talk to scientists, people who do imaging, users, I'm getting asked quite a lot, actually, is it possible to go faster? And the answer is normally something along the lines of, yes, but this is sort of the trade-off that you need to make. And there's quite a few questions you have to ask when you want to determine, are you able to image faster? Things like, first simply, how fast would you like to image? And can you even image that quickly? Some of these things are dependent on the sample that you're imaging, what your photon budget is, how much signal do you have, or even how much signal do you need to be able to achieve, the appropriate signal-to-noise ratio, or the quality of image that you're trying to get to. How many images can you image at a time? And this starts to lead you towards the idea of there's certain parameters and certain axes of performance that are really important to be able to truly achieve this ability to image at high speed. And the thing about scientific cameras is that they sort of require you to prioritize what you need, to be able to make the trade-off in terms of how many samples or cells do I want to be able to see in a single frame, because I'm normally reducing the size of this frame so that I can get to the frame rate that I want. And you're constantly performing this balancing act, going to extremes at times, to only seeing, parts of the sample or the cell that you're trying to image, just to be able to capture those dynamic events. And so we sort of set ourselves a challenge. Basically, how do we make the fastest camera? And it's sort of an interesting question, because people can define speed in different ways. Straight frame rate, right? Purely frames per second determines how fast my camera is. For some users, the interframe time, the time between frames, is the critical piece. I want sub microsecond time resolution between two events so that I can determine what happened exactly when, or the cycle time, or data points per cycle. So we define speed as being able to collect as much data in a single image as fast as possible. And when we set it that way, it kind of laid the challenge out to us quite simply, right? And from then on, our goal was, how do we make the fastest scientific camera? And this led us to the idea of, well, we needed a large sensor, right? Because we didn't want to trade off the area when we needed the higher frame rates. And to kind of put this into context of why area as well as frame rate are sort of interrelated, going back to the typical CMOS camera, 4 megapixels, 100 frames per second. Now, let's say we take that 4 megapixel sensor and we double its size, and it's now an 8 megapixel sensor. Let's just say we've doubled the number of rows, just to keep it simple. Now, your frame rate, if you kept everything the same speed, instead of going 100 frames per second, you're going 50 frames per second, because you have twice as much data, but the sensor itself is running at the same speed. So if you double the number of rows, you also have to double the frame rate. But by doing that, you're now an 8 megapixel sensor that goes 100 frames per second. Have you actually improved the frame rate? Only if you compare it to the original, right? But what people want to be able to do is use this whole sensor at frame rates that are higher than what they were previously able to achieve. So what they would want is this 8 megapixel sensor doing more than 100 frames per second. But there's other challenges that come with this too. You need to be able to see what you're trying to image. The faster you go, there's a proportional reduction in the amount of light you're able to collect per frame. Not only that, you need to be able to image well. It must look good. You need to be able to maintain this large sensor with the speed, with high sensitivity, but then you also need to have an appropriate resolution, right? EMCCDs in previous days had huge pixels, and that was acceptable because it allowed you to see what you wanted to, and image at a high enough rate, but you were almost always subsampling the object you were trying to image. And we wanted to ensure that you had this balance of being able to collect as much light while also being able to resolve and see the finer details of the samples you're looking at. And so it leads you to a pretty, that's why we called it a challenge, a pretty demanding requirement of what we needed was a really large imaging area. And this large imaging area needed to have a frame rate that was faster than what we were already able to deliver. It needed to be sensitive, and it needed to have high resolution. And so we spent quite a few years on this challenge, and where it led us to was the Kinetix scientific CMOS camera. Now, in yellow here, you have that typical SCMOS device, the 4 megapixels running at 100 frames per second. And with the Kinetix, you get a 10 megapixel, roughly a hair over 3K by 3K device with the 6.5 micron pixels, sort of this optimal size that's worked quite well for low light imaging while balancing the need for resolution. And we've developed this 10 megapixel camera in a 1-to-1 imaging ratio, just because it allows you to capture more of the imaging area. And we've been able to do this extremely large sensor with lots of pixels, and we've been able to get it to run at 500 frames per second. And to give you an idea, kind of how these speeds and sizes of the sensors have changed over time, starting off with a typical EMCCD 512 by 512, 16 micron pixels running at 67 frames per second was sort of, at the time, pinnacle of high-speed imaging, where you had the sensitivity, you had what you could call resolution and frame rate, which then took you to the typical CMOS device, which we have now sort of surpassed again with the Kinetix, where we've gone to a larger area that runs 5 times faster, and an area that is, about a hair under 2.5 times larger. So that would mean that you would get, conservatively 2 times more samples in a single frame, while being able to maintain the high-speed imaging capability of being able to see those extremely dynamic events. This is not even considering the potential of being able to then further region down this large sensor to go significantly faster than just 500 frames per second. Now, having a large sensor in a 1x1 format that captures a large amount of the available field of view, we found that it's perfect for large samples as well, allowing you to take less images at a time to be able to capture the whole image. And I think that outside of being able to just simply capture more dynamic events, you're also now able to you have to take less captures to be able to capture or image as many objects as you wanted to before. To give you an idea of how these diagonals or the areas of the sensors have changed over time as well, the typical CMOS camera has a field of view of roughly 19 millimeters. And we've now increased that to 29, or just under 30 millimeters with the Kinetix camera. Now, for scientific cameras, there's always inevitably some performance trade-off, and we wanted to architect the Kinetix in a way where this trade-off is minimized as much as possible. And so, what we ensured that there were 3 modes that a person could use when using the Kinetix camera, each optimized for a specific use case. We have the dynamic range mode, sort of the name speaking for itself. It's the mode with the highest full well capacity, where it's able to detect high and low signals in one image. Now, the trade-off that I was referencing was simply, typically the more bit depth you have, the larger the trade-off in frame rate you have to experience. And so we wanted to ensure that even with this 10 megapixel sensor, if there was a need for a high full well capacity, a lot of dynamic range in your imaging, you had the option. The slight trade-off there being that it runs at about 83 frames per second. Now, keep in mind that this 83 frames per second is at that full 10 megapixels of sensor size. And it goes back to the challenge of, the larger the sensor, the more the increase in speed there has to be able to keep up, giving you your expected high levels of frame rate. The second mode is the sensitivity mode, and this is simply the highest sensitivity mode. It has the lowest read noise and allows you to push the limits of detection. And this mode runs at 88 frames per second. And then lastly, the mode that we'd really designed the Kinetix camera for is the speed mode. Again, speaks for itself there in terms of its name, and it's the mode with the fastest speed. Now, it is also an 8-bit mode, and one of the reasons that we went with an 8-bit implementation is that it allows you to half the data storage. And this goes to how Microsoft Windows handles data. When you have an 8-bit image, it gets stored as 1 byte. If you have a 9-bit image, it will get stored as 2 bytes, or 16 bits worth of data. And by allowing our design team to go to this 8-bit image, it's allowed us to ensure that we can get all of this data out of the camera into the computer. The 500 frames per second at 10 megapixels at 8 bits is generating about 5 gigabytes of data per second. And if that had been 9 bits, that would have been 10 gigabytes of data per second, even from that 1 extra bit. And challenging, it really pushes the limits of the computer system already as an 8-bit image, and adding that 1 extra bit would make it almost untenable in terms of being able to handle and process that data. Now, in terms of comparing these speeds, the sort of baseline, like we've kept mentioning, is this typical CMOS camera. And so a typical CMOS camera at its 4 megapixels is running 100 frames per second. And if you took the Kinetix and took it down to the same number of rows or the same array size, you'd see that we would run at 130. So about a 30% improvement there. Similarly, with the sensitivity mode, if you compared the Kinetix to a camera that has one of these lower read noise modes, for example, on our prime BSI camera, we have a 1 electron read noise mode that runs 43 frames per second. The Kinetix in that same sensitivity mode runs 138, a significant improvement in the low noise, high sensitivity imaging mode. And then finally, we have the speed mode. This is where, if you look at EMCCDs and typical CMOS devices, the Kinetix sort of 5 times faster than a typical CMOS device, not even counting the fact that it's 2.5 times larger in terms of area or number of pixels. 4 megapixels to 10 megapixels, and that sort of leads you to this question of how am I then supposed to properly compare different technologies or different cameras that have different array sizes? Should I just simply do it off of frames per second? And now, that's always an option. But one of the calculations or specs that we started using internally was this idea of megapixels per second. We are considering the total amount of data that a camera is able to generate and acquire for you. And when you look at this megapixels per second and compare it to a typical CMOS device, you can see that the Kinetix cameras in all 3 modes, and especially the speed mode, have a significant advantage in terms of the amount of data that they're able to collect. Going back to what I said with regards to it needs to still be sensitive because you're getting this proportional reduction in frames per second. The Kinetix camera is a back illuminated sensor. So it does provide you with the highest levels of sensitivity, getting you, as close to perfect as possible within the visible range, with a peak sensitivity of 95%. And the advantage of this is that simply it allows you to collect as many photons as possible in a given amount of time. And the immediate advantage there is simply it allows you to go faster because you're able to collect as much of the light there is as possible. But it also allows you in certain situations where speed might not be as critical to potentially reduce the phototoxicity by lowering your exposure times, lowering the amount of excitation that a sample has to endure to be able to collect your images at high levels of signal to noise. And so with the Kinetix, we feel like we really have pushed to remove as much compromise as possible, to give you as much performance in a single device as possible, where you have a large field of view, which allows you to image large samples, to get higher throughput, and I think Dan will discuss this later, to be able to do multi-channel imaging with significantly larger areas to each channel. The Kinetix, with its extreme speed, it allows you to optimize your acquisitions with the 8 bits of the mode, and also to then deal with 5 gigabytes per second. And the 3 modes of the camera really allow you to optimize which mode makes most sense for your given imaging requirements at that time. So we really feel like with the challenges that high-speed imaging pose, just in terms of being able to push the technology to achieve this sort of really high level of performance, we feel that the Kinetix has really done that. And to take you through the Kinetix sort of in a outside of just PowerPoint slides, we're going to take you through a live demo of the product as well. The camera will be run by Dan, who's in our Birmingham office, and I will narrate, kind of taking you through the features and capabilities of the Kinetix camera.
Thanks, Rachit. Hi everyone, I'm Dan, and I'm going to use the microscope now here with the Kinetix to show you the capabilities of the camera live. So, to start with, we'll be using Micromanager as our image acquisition software. For those of you unfamiliar with it, this is a free software capable of controlling almost all cameras and other microscope equipment, and it's what we're going to be showing the Kinetix in today. For a brief introduction, you can see how we can go live on the sample here and how we can take single images, snap or album. And you can see here where we set our exposure time. And you can see here on the right the settings that we've chosen to use with our light source and our camera. So we've got a few different choices of wavelength, and we're able to choose the different modes on the Kinetix here. So just to check everything is working, let's go live. And here we have a really nice, beautiful image of our fixed sample slide with a 60x oil objective, and we're getting the full field of view of the Kinetix, which you can see up here. It's 3200 by 3200, so that's the full 29.4 millimeters. And you can see the speed readout here on the bottom going 50 frames per second, of course, because we set a 20 millisecond exposure time. So I'm going to hand back over to Rachit now, who's going to talk you through what we're doing here while I control the system.
Thanks, Dan. So what we have here is a great looking image. But what we want to be able to do is to put this image, which is using this large field of view, into a context that's easy to understand, right? In terms of the applications where this field of view is actually quite useful. So for example, if we take cell counting, as I'm speaking, Dan is switching to a 10x objective where we will take a look at some DAPI state nuclei, and we'll see how many of them that we're able to fit into a single field of view. But to give this some context, we want to be able to compare the fields of view to the main imaging technologies that are currently being used. And so it's still very common today to find CCDs being used in labs. Lots of companies still sell them today, including our own. And one of the most common sensors that was used was the Sony ICX285. It also had a 6.45 micron pixel and was 1.4 megapixels. And so what we can do is we can apply a region to the Kinetix camera to show what the effective field of view of a CCD would be. And what you end up with is this 11 millimeter diagonal. Now, CCDs are great cameras, but it's pretty easy to see that the size of the sensor is limiting us here, right? We're not seeing the whole sample. We're not being able to image as much of the microscope as possible. So 7 to 8 years ago, might be a little bit longer now, scientific CMOS was released and announced and was available to users, which gave us a much larger field of view. 2K by 2K, which is great. It was an 18 millimeter field of view. But the camera was still limiting us. When we're choosing cameras and trying to match our optics, we're usually focusing on getting the best resolution, matching Nyquist, so that our camera doesn't limit what the microscope is allowing us to image. But for field of view, we've not necessarily been able to do that. The camera has always been the limit. And at the moment, we're only getting 18 millimeters of that field of view. So while we can match our resolution, we can't necessarily get all of the information that might be available. Whereas now, with the Kinetix, we can go out to the full 3200 by 3200 pixels, which gives us the full field of view, this field of view here of 29 millimeters. So we're capturing all of the information the microscope is giving us, and this is pretty fantastic. But why do we want this big field of view, and what does it give us? And so that's where one of the main advantages, is the ability to capture large amounts of information, to maximize that throughput. For applications like high content screening or light sheet, or any application where we're dealing with large tissue sections or large samples that we're tiling and stitching, the key point is, if you can get more information per frame, more data points, we're able to get more information at once. And so here, we can count the number of cells available in each of these fields of view. So as Dan goes through these thresholding steps, he takes that first CCD image, labels it CCD as you saw, adjust the threshold so that we can appropriately count the number of nuclei that he has in a single frame. And what he'll do is he will then add that to a measurement table that we'll show you at the end. He'll repeat these steps with the CMOS image here, which, as he runs this cell counting plugin that we have, labels the image CMOS, representing, the typical 4 megapixel 2K by 2K CMOS, applying thresholds, doing the measurements. And then finally switching to the Kinetix image, running that same plugin to do the counting, calling it the Kinetix just so that we're not confused, and applying the threshold so that we can count the number of available nuclei in the image. And so as you can see with the CCD camera, we had 63 nuclei in an image. With the CMOS, that went up to 178, as you'd expect with the larger sensor. But then that again more than doubles with the Kinetix camera, up to 380 nuclei in a single image. That is a big improvement in terms of the amount of data that you're able to get in a single acquisition from the camera. Now, the other side of large fields of view is people looking at really large samples. We've got a piece of plant root here that we acquired with a 10x objective, and on a typical CMOS, we're not able to see the full samples. We're not getting everything that this 10x objective is giving us. And with the Kinetix, we're actually able to see the whole sample, which makes the acquisition much easier, much more convenient. And it really allows us to simplify that. Now, the other advantage of a very large sample is if you want to do multi-channel imaging. For example, DAPI, FITSI, Texas Red, and then a bright field image or another wavelength that you might want to image as well. Now, there's a number of ways that we're able to do this. You could use a filter wheel. You can take, and then sequentially do your acquisitions. Take the DAPI, then the FITSI, then the Texas Red sequentially. The problem with that is that if we're looking at moving objects, we've got the time shift between frames. We might miss out on information, or we're not going to be able to do the localization between frames because something might have shifted. So what people want to do is to take a single camera like the Kinetix and split the frame into 4 channels to then overlay them. And you can do that with a 4-way splitter like the multi-split from Cairn. And as you can see, what we have here is we have the DAPI channel on the top left, the FITSI on the top right, and Texas Red on the bottom left. And then at the moment, we've got a blank image on the bottom right, but that could be that 4th channel that you're trying to image. And each of these regions is 1600 by 1600 pixels. We're still getting a very large field of view. About a 15 millimeter diagonal in each one of these. And maintaining that field of view, we can do 4 channels simultaneously with 1 data channel going into the computer. And you minimize any alignment issues or other hassles that you might have. And as you can see, it's quite easy to then break these images apart and overlay them on top of each other, giving you, a great looking image as well. What some people prefer to do is to use a multi-splitter device where they're projecting these 4 channels onto, 4 different cameras, for example. But there's generally quite a lot of challenges that can appear there. You have to synchronize those cameras together. You have to make sure that the triggering setup is done correctly. You run into issues of rotation or alignment. And on top of that, what you have is 4 cameras worth of data streams going into the computer. And, working with that can be challenging. The next thing that we'll be taking a look at is the Kinetix speed capabilities, the frame rates that it's able to achieve. And so what we want to do is compare to current cameras, right? And so current typical CMOS cameras are able to go at 100 frames per second with 4.2 million pixels, which is pretty good. But for the users and people that really care about the speed, people that are doing things like single molecule tracking, calcium sparks or calcium imaging, or using voltage sensitive dyes or doing optical mapping, for those sorts of applications, they generally want to go much, much faster. And so what we'll start off with is we'll be looking at these beads here that are currently diffusing in some liquid in a dish. And what we will be doing is looking at them in a field of view that is comparable to these typical CMOS devices. And so if we go to the 1 millisecond exposure, just to make sure that we're not exposure time limited on our frame rates, on the Kinetix, what you'll see is that we're going at about 780 frames per second. So we are over 7 times faster than the existing technologies, right? And so you're seeing this running live, looking at these beads at 780 frames per second. But beyond this, people, especially the people doing calcium and voltage imaging, they want to image or record their data at 1 kilohertz or 1,000 frames per second. And so on the Kinetix, what we can do is we can put a region of 1580 by 1580 pixels, so that now we're able to go at this 1,000 frames per second. And as Dan just adjusts the contrast there so that we can see these beads, what you can see is that frame rate is just a hair over 1,000 frames per second, and that's pretty that's pretty great considering we're imaging here at a 15 millimeter diagonal. Now, the final thing that we want to look at is for people that want to go very fast, even faster than this. And what people are used to when it comes to EMCCDs, for example, or other technologies where you have to sacrifice your field of view to go that much faster, one of the regions, or sort of a very common region size that they're comfortable using, is 512 by 512 pixels. And so it sort of makes sense to compare it to that size. If we take that EMCCD, for example, if you were at this 512 by 512 region, you would be imaging at somewhere between 55 to 70 frames per second. If you take that same 512 by 512 region on the Kinetix, you'll see that we actually end up at, as soon as Dan adjusts that exposure time, at over 3,000 frames per second, which is pretty fantastic considering that, we're able to image at this ridiculously high speed and do it with, 95% quantum efficiency, with a sensitivity that lets you capture and acquire the data that you would like to at that very high speed. And keep in mind that at the same region size, a typical CMOS camera is giving you about 400 frames per second or so. So the final thing that we want to take a look at is on the sensitivity side of things. We have a good range of cameras here at Teledyne Photometrics for sensitivity. We have the Prime 95B, the Prime BSI that offer 95% quantum efficiency, but there's often also a requirement for speed. And the thing to note is that typically when there's speed, there's a compromise that comes into play with regards to the read noise. For example, the 8-bit mode on the Kinetix has about a 2-electron read noise. So for the really lowest of light techniques, single molecule imaging, people using our cameras for spinning disk imaging or on TIRF systems, even wide field systems where researchers want to drive down the exposure time to minimize photo damage or phototoxicity, read noise can become very important in these situations. What we've done with the Prime BSI or our other CMOS devices was we implemented a mode called correlated multi-sampling, or CMS mode, where we are able to drive down our read noise to close to 1 electron, which makes it ideal for low light techniques. And so people using our cameras on wide field systems, spinning disks, or with single molecules really prefer to use this CMS, correlated multi-sampling mode. The downside is that this mode requires a compromise. It requires you to run at a lower frame rate. And this is a trade-off that's not just on our cameras. On all cameras, there's typically this trade-off of giving up the ability to image at higher speeds to do it at a lower read noise. But with the Kinetix, we've implemented a sensitivity mode where that trade-off isn't there. And so if we take a look at this 4 megapixel 2K by 2K region where we have a 18 to 19 millimeter diagonal, other cameras where they might be going at 20 frames per second, 40 frames per second, the Kinetix is able to achieve frame rates of 140 frames per second with that same low noise performance. Now, the other advantage, though, that then the Kinetix still offers you is you can go to the larger areas. You can switch to a 22 millimeter diagonal, right? The 22 millimeter diagonal is the field of view that the majority of microscopes on the market are able to image. And at this full 22 millimeter field of view, we're able to give you 120 frames per second, with a close to 1 electron read noise, 95% quantum efficiency. Furthermore, because the sensor is so large, you're able to go to a 25 millimeter field of view as well, which some microscopes are able to achieve. And at this full 25 millimeter field of view, we're getting over 100 frames per second. The advantage of being able to maximize the sensitivity without that trade-off of speed is key. And finally, if we go to the full field of view of the Kinetix camera, the full 3200 by 3200 pixel array, just a hair over 10 megapixels, to take advantage of that full field of view, with that great sensitivity, we're still at, about 88, 89 frames per second. And so to summarize with the Kinetix, this is a camera that what we wanted to do was, have a camera that could take, as much information in a single frame as fast as possible, remove all of these compromises, remove the need to prioritize as much as possible. And with the Kinetix, we feel like we've achieved that. We're able to give you the full field of view of a microscope, and we can do it with great image quality at unmatched speeds. And, it's a camera that we're extremely proud of. And from here, what I'd like to do is hand it over to Dan, actually, to take you through some more of the applications where we think that the Kinetix is extremely suited for. So, thank you for listening to me. And Dan, take it away.
Thanks, Rachit. So in this final section of our webinar, I'm going to talk a little bit about the types of scientific applications we've been seeing where speed is an important concern, or the types of applications we've found that people have been really interested in the Kinetix for. And I'm hoping that what you'll get out of it is an appreciation for the different ways some researchers define speed in their imaging, and show you some of the different ways that a high-speed scientific camera like the Kinetix addresses those challenges. So one of the first things that I want to say is that we've found people doing high-speed imaging in so many applications and using a multitude of imaging techniques. High-speed imaging isn't restricted to a select few high-speed applications. You find implementations of it everywhere, from microfluidics to spinning disk, confocal to single molecule imaging. There are examples everywhere. So what I'm going to do is break it down to 3 specific application areas that use speed in different ways to achieve their imaging goals, to hopefully illustrate the different types of speed there are. So the first of these I want to talk about is calcium and voltage imaging. And that's because this is a great example of an application that focuses on pure speed or high frame rate recording. Now, So I'm going to give a brief introduction to it, as I will for the other applications too. But calcium voltage imaging is typically used in neuronal, cardiac, or skeletal muscle cells to investigate action potentials, calcium sparks, or calcium transients. An action potential, just to explain, an action potential is basically a nerve impulse. So that's when you get your signal from a nerve cell to make another cell do something as an action potential. And the duration of an action potential, it can be as low as 1 millisecond. So we're dealing with incredibly fast events. Voltage imaging can be used to directly measure the action potential, so that means you need to perform it incredibly quickly, and you'll typically be performing voltage imaging at over 500 frames per second. One of the other parts of it is calcium sparks and calcium transients. Now these are both parts of cardiac cells, and calcium sparks are small events that occur in cardiac cells that are often the precursor to a larger calcium transient, which is where the intracellular calcium concentration rises considerably to result in a muscle contraction. You can see here the calcium spark is typically less than about 40 milliseconds in duration, so that's an incredibly fast event. And a calcium transient, or the calcium transient, can have a time to peak, so that's basically from your point of low calcium to maximum calcium saturation in the cell, of 20 milliseconds or less. So again, an incredibly fast event. And you want to record calcium sparks and transients at a much faster rate than this to accurately measure calcium release and transient amplitudes, which means typically imaging over 1,000 frames per second or 1 kilohertz. An important thing, though, to remember with these techniques is that you need the speed in combination with a larger field of view, typically. And that's to maximize the amount of data captured, and to allow imaging of entire neural circuits, for example. But of course, the classic method for increasing frame rate was to make a smaller region, which was a compromise that needed to be made because the speed was the most important thing. And this is why we've been seeing a lot of interest in the kinetics in this application field in particular, because the speed can be achieved or even exceeded in a much larger area, a much larger field of view than used to be possible. The other thing about high speed is high speed requires low exposure times, so that means less signal coming from the sample, and that's where the back illuminated 95% quantum efficiency and low read noise come in, to make sure that when we are imaging fast, we can still detect our sample and acquire images capable of the quantitative data analysis that needs to be done afterwards. So the next application I want to talk about is light sheet microscopy. So again, to give a short introduction, light sheet microscopy uses a sheet of light to illuminate a single plane of a sample, which is then scanned through the sample to form a three-dimensional image. It's incredibly kind to samples. One of the key features of light sheet microscopy is that your chances of photo damage are extremely low. You can image samples for long amounts of time, which makes it unique as a technique. What it also does, it allows you to image in 3 dimensions. So that means that light sheet requires speed for a slightly different reason to calcium and voltage imaging, and that's because we're adding that extra dimension in. So because most light sheet is performed to give you a 3-dimensional image, we're no longer dealing with just X and Y, we've added Z. And that's because imaging fast in 3 dimensions lets us see the whole biological system rather than just a single plane. But of course it requires speed because it's capable of both very large and extremely fast image collection. Some modalities of light sheet are only limited by the speed of the camera. The image that you can see there on the right, for example, that is a maximum intensity projection of a cleared mouse brain. Now this is a huge sample. You can see from the scale bar there, this is about an 11mm by 11mm sample we're looking at here. It was acquired, I think, on like a 1.2x objective. And this was 500 microns deep, as well as this 11 by 11 millimeter X and Y. And the total time it took to acquire this image, this huge image with quite a thick sample, was 8 minutes. And I don't have the figures, but if you were to do that on, say, a point scanning confocal, you would be waiting a lot longer than 8 minutes. So it's an incredibly fast technique, and one of the big points about speed with it is that you get to do this sectioning, these Z stacks, so you can build up a three-dimensional image, and that's one of the things you need the speed for. And of course, the reason that we want to watch these things, that we want to image these things, is because living things are dynamic and ever-changing. So the faster that we can image them and the deeper that we can image them, the more of these processes we can see, which is why we're seeing a lot of light sheet, more and more light sheet being done faster and bigger to see more and look at these dynamic processes. Now, there's another type of light sheet, another modality that I'd like to discuss, which is interesting because it pulls in another type of speed as well. And that's digitally scanned light sheet. And this is a modality where you synchronize the sweep of the light sheet with the rolling shutter of an CMOS camera. And this is interesting because it's challenging to do at speed. And that's because you're usually limited to a single direction. If you can imagine it, you've got your light sheet on this example here on the right coming down. So your light sheet is going down through the sample, and at the same time your rolling shutter of your CMOS camera is going down through the sample at the same time. So you end up with the beam waist being in focus and the beam shoulders being then out of focus. And so you only get that very high contrast image from that in focus region, which is great because you get a very high contrast image of of very big samples. But this is where speed comes in again, because speed can limit your data collection in this kind of a mode, because if you can imagine a typical camera working, the roll of the CMOS shutter only goes in one direction. Let's say in this case it goes top to bottom. So when you're sweeping your light sheet through your sample, you go top to bottom, and you synchronize it with the roll of the CMOS camera, but then you need to reset it to the top again to then roll down again with the camera, and that's slow because you're stopping your data acquisition to roll again. So with programmable scan mode on the Kinetix, we actually made it so that you can scan down, you can also scan up, and you can also alternate, so you can scan down, then up, then down, then up, and in that way you increase your speed massively for this mode, because you no longer have to reset it back to the top again. So again, not what you typically think of when you think of speed, but nevertheless it increases the speed of what it is you're trying to do. To show you what this looks like, I've created a pretty simple PowerPoint animation. So if you imagine here that the sample is the blue triangle there, as we sweep the sensor down, the triangle arrives at the camera in the right orientation and is output as such. Then when we sweep up the sensor, the triangle arrives at the camera the wrong way round. But with our programmable scan mode implementation, the camera outputs the image in the right orientation, so every image is perfectly aligned. So the last application that I want to talk about is high content imaging. Any kind of imaging can be high content. This isn't, like a specific application. If the objective is to obtain as much data as feasibly possible, regardless of the imaging system, the sample, the magnification, or the fluorophore, as long as the main aim is to maximize data capture, you're probably doing high content imaging. This is often done with multi-well plates, so like a 96-well plate, so you can image lots of samples one after another extremely quickly, and sometimes do multiple dimensions and multiple channels. So it's most useful for these high throughput applications, so you can maximize the data collection for a better statistical analysis. So you've got examples such as in drug discovery, imaging dense tissue with high mag stitching, and lab on a chip imaging, which is also pretty interesting. So like the other applications I've spoken about, we want to go fast. We want X, Y, and Z dimensional information here. You do want to get that depth information in your samples as well. But you also want to add potentially multiple channels, like in the multicolor fluorescence image you can see on the right here. So we then have the time required say you're using a multi-well plate, you then have the time required to move to the next well as well, to take your next set of images. So speed really in this case means minimizing downtime. So it's another definition of speed, but also an incredibly important one. Because with high content imaging, with so much data that you want to acquire, the faster and the larger the amount of data that can be captured, the better. So a high frame rate is a given because you can capture your X, Y, and Z information faster. But a large field of view is also important because you can maximize the amount of data acquired in a single acquisition. So you don't want to waste time acquiring extra images to tile and stitch if you don't have to. And that's where the Kinetix can make a big difference to efficiency and throughput in high content imaging. So, to summarize what we've presented in this webinar today, high-speed imaging, it's a multifaceted challenge, and it will always involve some amount of compromise. And in many applications, speed alone is never the only concern. And as we just saw, different applications need speed for different reasons, and there will almost always be an additional benefit, whether that's the additional field of view that's needed, or the sensitivity that's needed, or the resolution that's needed. It's very rare that speed is needed in a vacuum. And when we created the Kinetix, we created it specifically to address these challenges with the unique combination of specifications that feature the extremely high frame rate, the massive field of view, and the back illuminated low read noise sensitivity. And on top of that, the ability to use the 3 different modes on the camera to further optimize based on experimental requirements. So thank you very much from both me and Rachit. We're going to be around for the next 10 minutes or so to take questions. So again, thank you, and please ask away.
Okay, some of those questions are rolling in. I guess we can get, Dan, do you want to just kind of go through the questions and we can kind of answer them as we go?
Yeah, absolutely. So let's start with a couple of quick ones, just to get some quick answers for you guys. What is the size of the camera pixels? The Kinetix has 6.5 by 6.5 micron pixels. Another quick one for you, Rachit. Where is the data stored? On the camera or streamed?
It is streamed straight to the PC.
Cool. Another one, when we have on the Micromanager software, actually. So Micromanager is a free software to control your camera. Does this software also allow you to do tile and stitch operations? Now, I believe that it does. Rachit, do you have other information? I've definitely seen tile and stitch applications been done with using Micromanager before. I don't know the exact way you'd have to do it without a little bit of reading, but I'm pretty sure I have seen it. Rachit, have you?
Yeah, as long as you have the hardware that goes into Micromanager that will allow you to do that tile and stitching as well, then yes, it should allow you to do that.
Perfect. So a bit of a bit more of a complex question, which I'm also going to send your way, Rachit. So an 8-bit mode, does an 8-bit mode have enough dynamic range for real imaging?
I think the short answer is yes, but it also depends on how the quantification happens. So if you keep in mind 8 bits is roughly 256 different intensities of light there. You want to be able to have enough intensity resolution, so it's not that each one of those intensity levels is an extremely large amount of signal, and so there is a bit of a trade-off there with the maximum amount of signal that you're able to measure is reduced. But I think in terms of does it have enough dynamic range, yes. Plus, if you're using the 8-bit mode, you're going extremely fast, so the amount of light you would have per frame is also reduced.
Yeah, exactly. And I've seen the same thing when I've been out in labs with the camera myself. It's when you're going extremely fast, obviously your exposure times are low, the amount of light you're acquiring is low. So you're only actually using that very bottom end of the dynamic range anyway, which is perfectly within the realm of where we have our 8-bit mode. So yeah, it has been used successfully quantitatively as well. Another quick one, how compatible is Kinetix with LabVIEW packages? That's one for you, Rachit.
It's compatible. We have a Teledyne Photometrics LabVIEW adapter on our website that you can go download now. It's freely available, so it should be fully usable in LabVIEW.
Perfect. So an application-specific question here. So in terms of single molecule imaging at high speeds, what is the most important or limiting factor in modern SCMOS cameras? For example, is it read noise, quantum efficiency, pixel size? That's a really great question because it's entirely dependent on the application. As with all these things, whenever I visit a lab with the camera, it's always okay. So you're doing this, but what exactly specifically are you doing? For some people, doing single molecule imaging, the field of view is very important because they want to maximize the number of molecules they're looking at. For some, they don't care about field of view at all, and they'll happily shrink right down to look at, say, a strand of DNA that they want to look at individual fluorophores landing on, and in which case they can go super small, and then they can boost their frame rates right up in that way. Generally speaking, what I always see with single molecule imaging is it is low photon count, is very low signals. So generally speaking, what we've seen to make the biggest difference in terms of single molecule imaging is particularly with the Prime 95B SCMOS camera, which is another one of our cameras, has been increasing sensitivity through the 95% quantum efficiency, the back illuminated sensor, but also the larger pixel size. As this was typically done with EMCCD cameras in the past, which had a larger pixel, the fact that the Prime 95B has a larger pixel and is a back illuminated CMOS, we often found made one of the biggest differences for single molecule imaging and caused most people we've visited to change from EMCCD to SCMOS to take advantage of the larger field of view or the larger speed or the increased resolution. Another one for you, Rachit. So how do you handle the field of view limitations of microscope optics?
So what I would say is the microscope that Dan was using today is a Nikon TI2, which the optics on that stand have allowed us to use the full field of view of the Kinetix camera. But otherwise, I would say that having the ability to region down and still have significantly improved frame rates over those typical SCMOS cameras is a pretty good advantage there. It's always a little bit more helpful to have more area than you need and to be able to reduce it than have the opposite problem of not having enough area.
Yeah, absolutely. So what mount does the camera come with then to access the full sensor size?
So the camera comes with an F mount. But the way that we've designed the camera, the mounts are actually swappable. So you're able to remove that F mount and screw on a T mount, which is just a very large C mount, if you will. And then if you have a microscope stand that doesn't necessarily have an F mount or T mount compatible adapter, it does also come with a C mount front, which you can then use on the Kinetix, with the condition that you'll have to reduce the effective field of view down to 22 millimeters at the most.
Cool. Thanks, Rachit. So last question. I'm afraid we're short of time, so it's just one more question I'll be able to answer. But yeah, I will make sure to follow up with everyone who has asked questions. Myself and Rachit will send you an email with answers to your questions after the broadcast. Don't worry, your questions will be answered. The last one that I just want to address then is, well, where can I get information about these cameras? You can get information about all of our cameras on our website, photometrics.com. If you go to the products drop down at the top, you'll see the Kinetix right at the top of it. That'll give you a full breakdown of all the specifications, applications information, and other cool stuff in there that you can use, like a calculator that we've got that lets you set, for example, a speed that you would like to achieve, and it will tell you the region size that you should be using for that. And the other way around, if you set a region size, it will tell you the speed. So some cool resources on there. But if you just go to our product section on our website, you can find out even more about this camera and our others. So thank you again, everyone, for attending. I will follow up with the rest of you who've asked questions after the broadcast. Rachit, do you want to sign off as well?
Yeah, absolutely. Thank you all for taking the time to attend, and glad that you could be here, and hopefully this was helpful, and the Kinetix is something that is interesting to you.
Cool. Thank you, everyone.
Thanks, everyone.